Hi, everyone, and welcome. It's great to have you here for our webinar, which is entitled Enabling the Future Printable Sensor for Sustainable Intelligent World. It is organized by Nanofutures and Physics World, two publications of IOP Publishing. I'm Dr. Vincenzo Pecunia, an associate professor at the School of Sustainable Energy Engineering, Simon Fraser University, Canada, and I'll be chairing today's session. Well, thanks for joining us. Indeed, this webinar is a great chance to connect with top experts in printable materials for next generation sensors, which have huge potential to help us move toward a more sustainable future. To start, I'd like to mention what inspired the webinar. It is the recent roadmap on printable electronic materials for next generation sensors. It's a milestone publication that brings together the largest group of experts ever to chart the course of these exciting technologies. It was authored by 108 experts from 15 countries across 4 continents, representing 57 different institutions. Together, they contributed to a total of 44 sections, each focusing on different classes of printable materials and sensors, which can detect light, ionizing radiation, mechanical stimuli, temperature, gases and vapors, as well as chemicals and biological substances or signals. While it would be wonderful to hear from each of these experts today, practical limitations mean that we'll have one spokesperson to represent most of these sensor types during today's webinar. I'm chairing this webinar as the lead author and co-organizer of the roadmap, and I'll also start off the discussion by introducing the general themes of the webinar. After that, I'll leave the floor to Professor Hersom from Northwestern University, US, who will tell us about printable light sensors. Next, Professor Iorcescu from Wake Forest University, US, will present on printable radiation detectors. And following that, Professor Young from the University of Manchester will share his insights into printable 2D materials for mechanical sensing. Next, Dr. Petti from Free University of Bolzano, Italy, will discuss printable gas and vapor sensors. And then Professor Franklin from Duke University, US, will delve into printable biosensors. After that, it will be your turn to contribute to the webinar by asking questions and sharing your thoughts with the panelists. And in fact, this is going to be a major highlight for our event. Without further ado, let me kick off the discussion by introducing printable sensors and how they are closely linked to creating a smarter as well as more sustainable world. On the path to sustainable development, a key question is, how can we use resources more efficiently and more equitably, whether in buildings, in cities, manufacturing, farming, or just about anywhere else? The UN Sustainable Development Goals capture this idea perfectly, emphasizing that sustainability touches every aspect of our lives, from food production and healthcare to water and air quality, responsible consumption, energy, of course, and much more. In this context, embedding sensors in everyday objects and environments offers great potential for advancing sustainability goals. Sensors can empower us to smart pattern spoilage and enhance access to clean water and air via environmental monitoring. And these are just a few examples. By widely integrating sensors to the Internet of Things, we can drive innovations like intelligent homes, smart cities, Industry 4.0, e-health, and precision agriculture, to mention but a few examples. Indeed, a recent World Economic Forum survey revealed that 84% of current Internet Development Goals. For sensors to turn these possibilities into a reality, however, we need a vast number of them. Indeed, around 45 trillion sensors are projected to be required in the near future to unlock the full sustainability potential of the IoT. As you can appreciate from this plot here, it represents that projection over time. But can current electronic technology keep up with that demand? Well, if you looked at new smart products with embedded sensors, and in fact, deploying conventional sensors at the scale needed for impactful sustainability applications remains largely prohibitively expensive. And this is primarily due to the complex, energy-hungry, and resource-intensive processes involved in making conventional electronics. And let's not forget about environmental impact. For instance, this plot captures the carbon footprint of a major automaker in gray, this line in gray here, highlighting how the electronics industry currently has a considerable environmental footprint. And this again is largely due to the complex, energy hungry, and resource intensive processes involved in making conventional electronics. But what if we could make sensors like we paint, using a palette of inks instead of the complex manufacturing processes of traditional sensors? That would really simplify things. It could cut down and greener. And this kind of innovation is key to deploying sensors at the scale we need for a smart sustainability revolution. Indeed, this is exactly what's fueling research into printable sensors, which are sensors made from inks of various printable materials. And thanks to their simpler and much lower cost manufacturing processes, they are uniquely positioned to lead the charge in a smart sustainability revolution. Firstly, this involves harnessing the developed in recent years, and these materials can be widely customized to respond to the various stimuli, which makes them ideal for sensing applications. Here I'm just showcasing a selection of families of these materials. Importantly, engineering these printable materials is crucial for creating high-performance printable sensors. Another important aspect is that to mass produce the sensors, we'll need to use printing and coating methods, which are the industrial analog. Here are a few examples of printing and coating methods used in printable sensor research, each with a unique way of depositing the starting ink onto the target substrate. Developing printable sensors is just as much about engineering this printing and coating processes as it is about engineering the electronic materials themselves. Certainly, developing new printable electronic materials and sensors comes with its own set of challenges, including sensitivity, stability. In our recent roadmap, we provide guidance on how to tackle these challenges, and today's webinar will give you a sneak peek into this, as our globally renowned experts will share insights into some of the most exciting printable sensor technologies out there. Now that we've discussed the importance of sensors made from printable materials and their relation to sustainable development, let's dive into the different types, starting with those that detect light. These sensors are crucial for sustainability focus on our daily lives. I'm therefore honored to introduce Dr. Mark Herson, Walter P. Murphy Professor of Materials Science and Engineering, Director of the Materials Research Center, and Chair of the Materials Science and Engineering Department at Northwestern University, US. He's a pioneer in nanomaterials, additive manufacturing, nanoelectronics, scanning probe microscopy, renewable energy, and quantum information science. Well, thank you for joining us, Professor Herson. The floor is yours, so please full presentation.
Great. Thank you very much for the kind introduction. I have shared my screen. I hope it looks good. If not, please speak up. So again, thank you all for joining us today. As you heard, I'm going to be focusing on printable photodetectors, and since we have limited time today, I'm going to focus specifically on the realization of these photodetectors using 2D nanoelectronic inks. The motivation of this work is as follows. The field of two-dimensional nanoelectronic materials has demonstrated superlative properties in device prototypes on idealized research samples, often isolated using the so-called Scotch tape method. Meanwhile, as Vincenzo already alluded to, the print electronics field has already shown roll-to-roll additive manufacturing, largely based on organic and nanoparticle inks. And so what we're trying to do in this effort is to unite these two fields, and in particular, design and formulate inks that combine the electronic properties of 2D materials with scalable additive manufacturing. To achieve this goal, we have to break it down into multiple sub-goals. The first is exfoliation. Typically, we're going to be peeling away or exfoliating these 2D materials from bulk van der Waals solids. We need to do that in a way that optimizes the yield, throughput, and flake size. We then have to formulate the inks, which will require engineering the solvents and possibly also stabilizing polymers to enable effective printing while also achieving adhesion and mechanical flexibility. The resulting structures are going to be much larger than the constituent nanomaterials, and as a result, they're going to be percolating networks. And consequently, the control of the film morphology will have significant control over the final properties, and this can be done via solvent evaporation and additional additives to engineer the final morphology. And then finally, we have to worry about interfacial properties, again, because these are percolating networks. For example, we want to minimize interfacial and contact resistance in conductive inks, maximize capacitance and minimize leakage currents for dielectric inks, and maximize mobility and switching ratio for semiconductor inks. The way this is typically done is to take your bulk van der Waals solid, put it into a suitable solvent, often add a surfactant or stabilizing polymer, and then agitate. And the most common incumbent method for this agitation is shear mixing. And shear mixing is a method which is quite effective. And in our lab, it's been scaled to the 20-liter level, utilizing inline shear mixing. But the catch is that this process requires recirculation for timescales on the order of a day to get reasonable yield. And as a result, while this looks like it's continuous flow, it's still effectively a batch process. And so what we've been doing in our lab more recently is exploring true continuous flow methodologies for agitating these solutions and achieving exfoliation. The one which is working best at the moment is wet jet milling. Wet jet milling takes your initial dispersion, splits it into two streams, which are then accelerated and collided together. The resulting turbulent flow then drives efficient exfoliation in a truly continuous flow manner. And while this method has been demonstrated previously, in this context, it's always been done using high boiling point solvents like N-methylpyrrolidone. This leads to some significant challenges from an environmental or sustainability perspective. And as what we've been doing in our lab is trying to utilize the wet jet milling method with different solvents that are more sustainable, such as bio-derived ethanol. This requires also the addition of stabilizing polymers, also bio-derived, such as ethyl cellulose. And in order to optimize the conditions of the wet jet milling, we use Bayesian optimization, which is a machine learning methodology that allows you to very efficiently explore complex and many variable experimental phase spaces. In this manner, we've been able to achieve very efficient exfoliation of 2D materials in ethanol, as opposed to the incumbent N-methylpyrrolidone. And by performing life cycle assessments, we've been able to show that this wet jet milling exfoliation allows significant reductions in greenhouse gas emission and fossil fuel energy consumption, in addition to effectively eliminating the human toxicity potential of NMP. This is definitely a green and sustainable process. The next step after you exfoliate is to isolate the well-exfoliated nanosheets from the poorly exfoliated bulk material. This has historically been done using centrifugation, which is also a batch process. And as a result, although the exfoliation is now continuous flow, we then slow everything down and have to do the separation using batch centrifugation. This method definitely works, but it becomes the clear rate limiting bottleneck, especially when the input is a continuous flow wet jet milling process. And as a result, I've been looking in our lab at alternatives to centrifugation. The one which works quite well is continuous flow cross-flow microfiltration. This is a methodology where you take your incumbent feed stream down the center of a cylindrical filter, where the primary flow is down the axis of the cylinder. But this is a porous cylinder, and as a result, as long as you have a cross pressure across the membrane, then you'll have a cross flow going perpendicular to the primary channel flow. And what will go through the cross flow will just be the small, well-exfoliated nanosheets. This method can occur in a highly continuous flow and high flow rate manner. What you're then left with is a isolation of your well-exfoliated 2D nanomaterials. But the issue is that is typically a relatively dilute suspension, not one which you can directly plug into a printing methodology. And as a result, you need to do downstream concentration. And you'd like to do that in a manner where you can harvest and recycle the excess solvent, in this case ethanol, and any excess stabilizing polymer, in this case ethyl cellulose. And that's done with a second cross-flow filtration step. This one is called ultrafiltration, where now the pore sizes on your filter are smaller than your nanosheets, and as a result, the nanosheets go down the axis of the cylindrical membrane. And what's pulled out in the cross-flow direction is the ethanol and the ethyl cellulose, giving you a permeate stream which can then be easily recycled, concurrently controlling the concentration of the dispersion to get suitable viscosity for printing. This use of cross-flow filtration compared to centrifugation also gives you substantial advantages in greenhouse gas emissions, water consumption, fossil energy use, and costs compared to conventional batch-based centrifugation, while concurrently achieving orders of magnitude higher manufacturing throughput. The bottom line is that we can produce huge quantities of these inks. The next step is to actually put them into a printer and see if they print effectively. What I'm going to show you now is printable molybdisulfide inks. Molybdisulfide is a semiconducting ink and therefore suitable for photo detection. And indeed, in this case, we're doing inkjet printing, and we can get very beautiful printed films and patterns without issues like coffee stain effects during drying. We then remove the ethyl cellulose stabilizing polymer using thermal or photonic annealing, giving us a conductive trace. Because these conductive traces are made out of semiconducting molybdisulfide, they are photoresponsive. And here I'm showing you with the light on and light off changes in the photocurrent. I note that the contacts to these devices are also created using printing. In this case, printable graphene is used as the contacts. And what we can see is that the performance in terms of responsivity depends upon not only the quality of the material, but also the way in which you do the curing. And that if you do thermal annealing, which is a relatively slow volatilization of the ethyl cellulose polymer, that gives you a very well-ordered morphology, which gives you fast time response, but relatively low responsivity. Whereas if you do photonic annealing, which is a much faster evolution of the ethyl cellulose, that leads to a more disordered matrix, which gives you a compromised time response, but gives you a much higher responsivity. The bottom line is that the way in which you do the curing also influences the final properties. But what I want to stress is that while these initial results were promising, the responsivities are really quite low. And the reason is that the ethyl cellulose-based exfoliation on its own only gives us control down to few layer MOS2, whereas if we got all the way to monolayer MOS2, we could achieve direct band gap behavior and therefore improve photo detection. And that has been achieved recently in our lab using what we call megasonic atomization. This was first demonstrated in an aerosol jet printer, where the way you create the aerosol jet is to do so-called megasonic atomization, which is aerosolization at megahertz frequencies. And what we observed after doing this for timescales on the order of an hour are clear changes in the optical properties of our inks, which manifests itself not only in the absorption spectrum, but also the photoluminescence spectrum, thereby confirming that we've thinned down to the monolayer limit. We now take that megasonicated molybdisulfide monolayer ink, we print it onto substrates. One challenge that we have here is that when the flakes are single layer thickness and micron in size, if you don't control the evaporation of the solvent carefully, you get crumpling of the molybdisulfide, which is suboptimal for charge transport and therefore photo detection. But by incorporating a small amount of high boiling point solvent, we can control that drying process. This giving us nice, large, thin molybdisulfide flakes, forming percolating networks without crumpling. And then if we use graphene contacts, we can achieve low resistance electrical addressability. And with these now optimized megasonicated molybdisulfide printed films, we get substantial improvement in photo detection performance. In particular, on the plot on the right, we can see responsivities that are orders of magnitude higher than what was previously demonstrated. This comes from the direct band gap character of the molybdisulfide. This is also done without compromising response time. Response times are now in the millisecond range, which is the best of what I showed you previously. And this is because the charge transport is effectively controlled by having these flakes going down flat in a morphology which facilitates charge transport. The last step is then to ask, can we scale up the megasonication process? This is work in progress. But what we've employed are megasonication baths, which are widely used in the semiconductor industry. We've been able to achieve the same level of exfoliation that we achieved using the small aerosol jet printer atomizer. The resulting flakes are quite nice. They're showing clear evidence for monolayer thickness in atomic force microscopy, photoluminescence spectroscopy, and Raman spectroscopy. These inks are giving us suitable performance in photodetectors, and I think puts us on the brink of now taking this to the commercial scale. So with that, I think I'm out of time. I'll quickly summarize. The first point I tried to make today is that continuous flow wet jet milling combined with continuous flow cross-flow filtration allows you to sustainably produce large quantities of 2D nanoelectronic inks. And then the more recent innovation of megasonication allows us to now exfoliate down to the truly monolayer limit, getting direct bandgap character, which is suitable for high performance printed photodetectors. With that, I will conclude, acknowledge my research group at Northwestern, all the funding agencies, and hand off back to Vincenzo.
Thank you, Professor Herson, for the very insightful discussion. It is now time to switch gears, and we'll be shifting to Dr. Ioana Iorcescu, who is going to be presenting on radiation detectors. So the floor is yours, Ioana, as you're ready. Thank you.
Thank you very much. I hope you can see my screen. Okay, so thank you for the invitation, and I will talk about radiation detectors and dosimeters with a focus on organic semiconductors. I come from Wake Forest University, and that is in North Carolina, United States. So radiation detectors actually are used in a wide variety of applications, from national security. Here you see an example of domestic use. Let me find my laser pointer. Domestic use of radiation detectors, and then they can also be used on the battlefield. They are also incorporated in a wide variety of healthcare applications, both for diagnostics and for treatment, as I will give more examples later. They are spread as safety elements, for example, to measure the exposure of workers that perform in nuclear plants or for medicine. Now, before we start, let's spend a little bit of time on vocabulary. I will talk about radiation detectors and also radiation dosimeters. The radiation detector is the instrument that is able to detect and identify the type of energy, these high energy particles. And on the contrary, radiation dosimeter is a device that measures the dose uptake of this external ionizing radiation. And the units that I will address in respect to dosimeters will be the units of gray, and 1 gray is 1 joule per kilogram. So if we make a comparison with rain, the radiation detector will tell us if it's raining or it's not raining, and then the radiation dosimeter will provide information about how much rain has accumulated. So within this roadmap that Vincenzo introduced, we have a chapter that is dedicated to printable ionizing radiation detectors and dosimeters. And then this starts with a nice overview written by Beatrice Fraboni with the different uses of printable ionizing detectors, from security in public buildings to cargo inspections, space missions, different types of testing, even relationship with cultural heritage preservation, and also medical application. The types of materials that are covered in this chapter span lead halide perovskites, lead-free perovskites, organic semiconductors, and printable quantum dots. And in particular, I will focus on radiation dosimeters for medical applications. The idea is to start with materials to understand what type of properties are needed in a material to incorporate that material in a large area device array, and that can address both the detectivity and the dose rate, then incorporated into applications that are conformal to the human body, that can be placed on different parts of the human body to address different type of medical applications. Now, let's talk about the medical dosimetry, the dose of radiation in relationship to the type of medical application that it can address. Very small doses, you see here in the tens of, like fractions of centigrades, are used for X-rays for dentals and limbs. A little bit higher, we have, for example, CT scans, which use radiation doses in the order of 0.4 to 2 centigrades. And then on the larger part of the spectrum, we have the radiation used in oncology in the order below 100 centigrade for diagnostics of cancer, and then few hundreds of centigrade for therapy. So radiation therapy is one of the most effective methods of treating cancer alongside chemotherapy. And the way it works, radiation will hit the cancer cell and then it will destroy or reduce the growth of these cancer cells. It is used in two different ways, either as an external radiation beam, as you see here, but also as an internal type of radiation active treatment. Now, we also know that exposure to radiation, if done not right, can be harmful. And what you see here in this table is the radiation dose and the impact on the human body. You see doses in the ranges of 0.5 to 1 gray are mild, and most likely the person will survive this exposure. However, as we increase this radiation, reaching to 20 to 30 grays, the impact on the human body is severe. And as you see here, unfortunately, that is certain within just a few days. So now there's kind of a discrepancy. I told you earlier that we use doses in the orders of grays for treatment, but at the same time, I'm telling you that orders in the orders of gray are harmful to the human body. And here you see some values that are used for doctors for head and breast cancers, and almost 100 gray cumulative total dose for prostate cancer. What's happening actually with the treatment, this dose is localized. So it's applied specifically to the point where the tumor is located, and only then we have this localized dose escalation of the radiation, and then the rest of the human body ideally is not exposed to radiation. So that's why it's very important to be very precise with respect to the magnitude of radiation and also the spatial location of the radiation. And that is because exposure of the healthy tissue surrounding the tumor, exposure to radiation can induce secondary cancer. And that actually happens quite a bit from what I hear from doctors. So we need high precision and we need very high spatial resolution simultaneously. And we need this to happen 100% of the time. 99% of the time is not good enough because we are talking about human lives now. So then it would be really nice to have this instantaneous feedback so that the doctors and technicians can adjust in real time this radiation location and dose, because a lot of accidents have happened. So this inaccurate measurement and again, these accidents can happen both because of human mistakes and instrument malfunction. So then if we can create a way to measure this dose better, of course we will have better patient outcome. The way that the dose is measured right now, so here you see an instrument that is used actually in the hospital for radiation therapy. The patient is placed over here, and then right here in red, and then down here also we have conventional dosimeters, which are based on silicon and germanium diodes, and then they are pre-calibrated based on the needs of the patient, and then the patient is sent in, and then a button is pushed, and then the patient is exposed to radiation. But technicians cannot see in real time the value of this dose. And then small movement of the patient can induce significant changes in the location. At the same time, there's inhomogeneities between different parts of the human body, bones versus tissue, and so on. And then again, we use these silicon and germanium diodes to measure this radiation. And they have nothing in common with the human body, except the fact that they are solid state, if we want to say that, right? So then, because this response is very different than that of the human body, there's a series of conversions that the software needs to do. And again, with a lot of conversions come a lot of room for error. So it would be really nice if we would be able to come up with radiations that have similar response to radiation as the human body. These materials are called water equivalent or tissue equivalent materials because they respond like tissue. And what you see here is the response to radiation of an organic semiconductor. It doesn't even matter what it is. In blue, and then in dotted black line, you see the response of the human body. Then for a very wide range of energies, you see that the response are almost identical. And why is that? Because they have similar atomic number. So they they absorb radiation in a similar way. Germanium and silicon, they absorb much better radiation. They are more sensitive, but it's different than the human body, so then conversions are necessary. So these organic materials can be seen as tissue equivalent materials. So then if we incorporate these materials in printed radiation dosimeters, we will have more precise and at the same time less complex medical equipment, overall improving the quality of the healthcare. At the same time, these materials will take advantage of the other attributes of organic semiconductors, low cost processing by a wide variety of printing techniques, solution printing, laser printing, and so on. Mechanical flexibility, they can be conformal to the human body, placed at the point of contact with radiation, and providing an avenue for adjusting the dose in real time. They are lightweight, so they are portable, wearable. So then we can think about this radiation treatment being performed in remote areas that are now out of reach for those cancer patients. And the power of organic semiconductors for radiation dosimetry has been acknowledged starting with, let's say, around early 2000s. So here you see a few examples of radiation dosimeters based on organic semiconductors, also incorporation on flexible substrate. You see a response. They can be done either by a direct detection, conversion of the X-ray beam into an electrical signal, or through this using a scintillator. And the sensitivity has increased in time as a response of better understanding of structure property relationships in related to sensitivity. But what I want to talk in the few remaining minutes I have is about the use of field effect transistors as radiation dosimeters. So this is the structure of the field effect transistor. We have the three electrodes, gate, source, and drain. The order of these electrodes can be different, either top or bottom. Then we always have a gate dielectric and a semiconductor. If the semiconductor is organic, then these transistors are called organic field effect transistors, or OFETs. And here I put down a tutorial that we have written a few years ago on organic field effect transistors. Then we can control, just like in a regular transistor, we can control the voltage between the gate and the source. We can control the voltage between the drain and the source. And with that, we can control the charge density in the channel. So we have used these transistors on large area flexible arrays. And we call these rad OFETs because they are related to radiation detection. And the idea is to place them again on the human body to validate in real time the dose being delivered. And this work is in collaboration with the Comprehensive Cancer Center at the Wake Forest Medical School. So we work with doctors, we work with physicists in solving this very difficult problem. So as I said, we build these large area device arrays. We can have 100 or even more devices on a substrate. This is one example of a material made by Professor John Anthony at the University of Kentucky. The problem is that in general, organic transistors are not very stable. So this means that in time, either because of exposure to environment or because of bias stress, the current voltage characteristics will shift. So here in black, you see the time zero current voltage. And then after certain stressors, you see this huge change. So then it will be very difficult to understand how much of this change comes because of the exposure to radiation as opposed to environmental or bias stress effects. So we have spent quite a bit of time to improve this stability that is not related to radiation. And as a result, we have created really highly stable organic transistors. And this is seen here in the very, very small threshold voltage shift upon very aggressive biasing in air, high humidity for a long period of time. So we took these transistors and we incorporated them in radiation detectors. You see here, we place them under the X-ray source, and then we can control the dose. And you see here that we have a shift in these current voltage characteristics, but now this shift comes solely from exposure to radiation. And we use this shift in the threshold voltage, VTH, as a measure of the response to radiation. And we can do that because this shift persists even after 95 days, 210 days, even after heat annealing. So it's quite stable, which allows us to come and back to the lab and measure the shift and do statistics. So if we follow the shift as a function of those, you see that first we have the threshold voltage becoming more positive and then more negative. So clearly there's two things going on. Here in red, you see the overall shift as a function of radiation dose. And then in black, we see the control sample. This is the sample that my student took in the backpack, exposed, and then measured again. The sensitivity is increased with the gate voltage. I will be a little bit quicker because I'm struggling with time. Okay, let me just go here. We took these transistors and we expanded them on very large area arrays. We can deposit these films using either spray coating or laser printing. In particular, laser printing is very appealing because it's a solvent-free type of printing. So then it's environmental friendly with a very small carbon footprint. We took these devices, we flexed them, they respond very well to radiation, and we try to also understand what's happening in the material such that it makes it respond to radiation. So we performed the trap distribution of states analysis as a function of radiation dose, and you see that here. And in summary, organic transistors can be used as organic dosimeters, and because they can be placed on a flexible substrate, they allow direct placement on the human body at the point of contact with radiation. And hopefully in the future, they will be able to provide a greater precision and a lower complexity medical equipment to make health more affordable to everyone. With this, I'm ready to pass over the ball to the next speaker.
Thank you, Professor Iuchescu. This was a very intriguing perspective on printable radiation sensors, and we're very excited about the latest results you presented. Well, if you have any questions for Professor Iuchescu, please drop them in the chat box, and she'll address them during the question and answer session at the end of the event. So now let's shift gears and explore how printable materials can detect stimuli, mechanical stimuli, particularly focusing on 2D materials. It's therefore my pleasure to introduce Dr. Robert Young, who is an emeritus professor at the University of Manchester, UK, and is a fellow of the Royal Society and the Royal Academy of Engineering. He's renowned for his pioneering research on the relationship between the structure and mechanical properties of polymers and composites. Thank you for joining us, Professor Young. It is a pleasure to have you here, and the floor is yours.
Well, thank you very much, Chairman. It's a great pleasure to be able to talk at this webinar. I'll just warn you that I'm actually giving this presentation from Southwest China, so it's nearly 2 o'clock in the morning, so hopefully I can stay awake along with the audience. Anyway, I'm going to talk about 2D materials for mechanical sensors. I'm from the National Graphene Institute, School of Materials at the University of Manchester, and I'm going to show how 2D materials can be used for mechanical sensing, and I've noticed there's really quite a lot of similarities with the first talk we had from Professor Hersham, who's using 2D materials in other applications. So, well, I think most of us know what graphene is. It's the basic 2D material. It has superlative properties. It has high stiffness, high strength, and high electrical conductivity. And we also know there's a large family of 2D materials related to graphene, such as hexagonal boron nitride, which is an insulator, molybdenum disulfide, semiconductor, as we saw, and mexenes. There's a whole family of these materials. And again, Professor Hersham showed that the materials can be dispersed in polymers and solvents to give printable inks, and also pastes and various other types of media. So there are some similarities, but what I want to show you first of all is the sort of current status, as I see it, of using 2D materials for mechanical sensing. And essentially, if you take any conductive filler and add it to a matrix, a particular polymer matrix, usually the polymer, of course, is insulating, so has a low conductivity. But as you increase the volume fraction of filler, conductive filler, then the conductivity shoots up through this percolation region, and then the material becomes conductive. So we get to something known as a percolation threshold. And this is where we can produce strain sensors with particularly high levels of sensitivity. So I want to show you about printable graphene sensors for strain measurements. And here's one example of one of our publications where we looked at what we call G-putty, which is graphene dispersed in a silicon polymer, which makes a very strain sensitive material. If you plot the conductivity of this material on a log scale, you'll see it's a log scale here against the volume fraction of graphene, you see that the conductivity is very low to start off with, then shoots up, say at about 3% loading, and then goes to a plateau value. And the sprayed material, the painted material, is actually much more sensitive than the bulk material, which is quite nice. The work was published in Science and Small. Now, when you deform the material, you find that the resistance increases, and the resistance increases pretty well linearly with strain. So now we have the essence of a strain sensor. But if you look at these curves here, the top curve is for the lowest loading, 3.6%, just at the percolation threshold. And that gives a very high level of sensitivity, which we call a gauge factor, and allows us to measure strain in great detail and great precision, a very high gauge factor. Now, what the mechanism is essentially, as far as we're concerned, is that we have a percolated network to start off with. We then stretch it in the horizontal direction. You get breaks in the junction points, the resistance goes up, and of course, if you let it go, it all springs back. And I've just got one example here of where we've used this material, and this is by using a strain sensor to put on the wrist. And you can use this graphene loaded putty paint or coating to put on a substrate, and then you put it on the where the pulse is. And if you measure the resistance as a function of time, you can see that it goes up and down. And if you look at it in more detail at the sort of 1 second scale, you can see that you're getting pulses about every second. And that allows you to measure both the pulse, and also from the shape of this curve here, you can actually also measure the blood pressure. And that's a very simple example of some sort of way of you can use these printable graphene sensors for strain monitoring. Now, that's the current status, and I want to talk about perhaps new developments. I'm not going to talk about real materials, although we had hints of how you can do it from Professor Hersham. There's two drawbacks of the system we have here. One is we've got wires. You can see there's wires connected to it. And secondly, you're just measuring the average strain over a sort of centimeter region. You've got no sort of localized strain measurements. So what I want to talk about for the rest of the talk is using a completely different way of measuring strain in these materials. And this is something we've been doing for quite a long time, using Raman spectroscopy for measuring strain, and I'll show you how that can be used and probably would lead to a new type of strain sensor. Raman spectroscopy, as most people probably know, is an interesting technique, very useful for 2D materials. You take a laser beam, you focus it onto a specimen, and you look at the scattered light. The laser spot size is about 1 micron, which is important. And you can get Raman spectra from most nanomaterials, particularly 2D materials. And you can characterize many aspects of the material, particularly you can use it for strain sensing. We have a very recent review on this in Progress in Materials Science. Now, here's just an example of just the exfoliated graphene, just the flakes of exfoliated graphene, monolayer, bilayer, trilayer. And first of all, you can see that you have quite different Raman spectra for monolayer, bilayer, and trilayer. Monolayer, you get this 2D peak is very strong, the G peak is weak. Bilayer, it's the other way around. The G peak is strong and the 2D peak is weak and also shifted slightly. So you can use it for counting the number of layers. And of course, that's not really anything to do with strain sensing, but it just shows how you can use the technique. Let's look at strain sensing. And here you can make a sort of model paint, shall I say, which is thin films of polymer sandwiching graphene monolayers. So again, it's a similar sample here. of a monolayer of graphene, which you can see in the optical microscope quite nicely, 10 micron scale here. And if you stretch the material, stretch the substrate in which the paint is sitting, you get this very large shift in the Raman band. So this is the essence of a strain sensor, this big Raman band shift. And that allows us to measure strain in a non-contact way. We don't need any wires. We can just shine a laser on it and we can measure strain. So let's show you a particular example for a single flake of graphene, although you can probably extrapolate this up to a sort of structure which we saw in the first presentation, where you've got lots of graphene flakes. Again, this is essentially a single flake of graphene. Sorry, just jumped. A single flake of graphene under stress in the vertical direction, and you can see that the Raman band shifts enormously when you deform the material over 1% strain. And if you measure the peak position of the Raman band against strain, you have this linear relationship. So you can just, once you know the peak position, you can read off the local strain. This is a sketch of our flake of graphene, and this is a flake of graphene containing a crack. And this is only 5 microns here. And you can see that this is where the crack is. And in the crack region, we have blue coloration indicating low strain. Then right at the crack tip here, we have a red coloration indicating strain or stress concentration. So you have the ability with great precision to map out local strains in graphene. And I think it's pretty easy to envisage a situation where you have graphene flakes in a paint type structure, and you can go around and you can map out local strains in the substrate underneath. So this is essentially how you could make a strain sensor using graphene. Now, what I want to do is, again, related to the first talk, but doing something slightly different. And that's looking at these other 2D materials, tungsten disulfide or molybdenum disulfide, which show luminescence. And luminescence is very interesting compared to the Raman spectroscopy, because essentially you use the same hardware, use the same instrument. So if you have, say, a tungsten disulfide crystal or molybdenum disulfide crystal on a substrate, you can get a luminescence spectrum. When we saw this, we also saw in the first talk that the luminescence is particularly strong for monolayer and then decreases in intensity as you go to bilayer and trilayer materials. So this spot 1 is monolayer, spot 2 is bilayer, spot 3 is essentially bulk material. And if you now deform the substrate, then these luminescence bands shift, and they shift just like the Raman's bands shift, and they shift linearly. So if you deconvolute the luminescence band, you can see that this is now the peak position of the luminescence band against strain. We get large shifts again. So we have the essence now of a strain gauge and a strain measuring system. And so this is, we saw some structures that were made by Professor Hersham, and you could see he was using it for a different reason, but if you want to use it for strain measurement, you could also do that with those sort of nicely distributed structures. And he showed particularly you could get high loadings of monolayer, and the monolayer is the best material for strain measuring. So it all sort of works out really quite nicely. And here's an example of just a single flake. Again, I'll talk about a single flake. This is a single flake about 2 microns long. And if you map the luminescence over the flake, here's the flake here, you can see that you get, and you stretch it in the vertical direction, you get a yellow coloration in the middle of the flake and blue at the edges. So you have a high strain in the middle of the flake and low strain on the edges. If you measure things along the line here, measure the strain along the line as shown over here, you get these data points from individual measurements, and you can actually map out the strain distribution theoretically using standard shear lag theory, which people use in composites. So this is for a single flake, but I think it's fairly easy to see a situation where you could have lots of flakes inside some sort of paint type structure, and you could actually use that for measuring strain with quite a high degree of precision. And we saw in the first presentation how you can actually produce those sort of structures, which I found very interesting indeed. So I'm now coming just to the end of my presentation. With these 2D materials, as far as actual strain sensors are concerned, printable sensors are available by dispersing 2D materials at the moment. And those sort of systems, you can measure strain from changes in electrical resistance. And you find that you can tune the sensitivity by the volume fraction of the material. And you can use these sensors for a variety of applications. The one I showed you was for blood pressure monitoring, but there's various other applications where you can use them. That's the current status, but looking into the future, I think here we have a completely different way of doing things now by using optical strain sensors that we don't need any wiring. We just have to shine a laser beam. We could either do it from graphene with Raman scattering, or we can do it with other 2D materials such as molybdenum disulfide, tungsten disulfide, and look and tune into the strong strain sensitive fluorescence bands. And there's various advantages of this technique. Particularly, we could measure strain in 1 micron regions, or if we defocus the laser, of course, we could take a more average strain. But that gives us quite a degree of sort of precision in our measurements and a new way of completely doing things. So I'd like to thank you for your attention, everybody.
Thank you very much, Professor Young, for those invaluable insights into the world of mechanical sensing with 2D materials. If you have any questions for Professor Young, please drop them in the chat box and I'll address them at the end during the question and answer session. Now let's turn our attention to printable sensors for detecting gases and vapors, which are crucial for sustainability-focused applications involving environmental monitoring, food sector, smart homes, and so forth. I'm therefore delighted to introduce Dr. Petty, Associate Professor in Electronics at the Free University of Bolzano, Italy, and recipient of the ETH Zurich Medal for her research in flexible electronics. Her work focuses on the design, fabrication, and characterization of flexible and printable sensors, energy harvesters, and thin film devices and circuits, with an emphasis on sustainable and low-cost materials in manufacturing processes. Thank you for joining us, Dr. Petty. The floor is yours. Thank you.
Thank you very much, Vincenzo, for the introduction, and I'm very pleased to be here and give this webinar. So the focus, as said, will be on printable gas and vapor sensors, and with an emphasis on those based on carbon nanotubes. So let's see if I manage to switch. This is kind of not working now. Okay, super. So the gas and vapor sensors are extremely important. I mean, this is a very growing market, which counts now for 1.5 billion USD sales in 2023, and those are expected to grow quite extensively to 2.3 billion by 2028. There are various application areas where gas sensors are extremely needed, and I have here this nice picture taken from the roadmap from one of the sections on metal oxide. As you see, there are quite a lot of different fields, but the most important ones are surely environmental monitoring, indoor and outdoor. So smart city, building automations are the main drivers. At the moment, we also see really the expansion of other fields, precision agriculture, also food quality and health applications. And of course, there are way more other fields. What is the most used device platforms for gas and vapor sensing is a very simple platform, chem-resistive sensors, which basically measures the changes in resistance upon exposure to various gases. It's a very easy to fabricate configuration. It allows the use of small quantities of active materials. We've seen this is very important in printable sensors. It has a wide absorption of the sensitive materials, and it has a simple data to read it. You see here an example of simple interdigitated electrodes with an active material. that are being exposed, in this case, to ammonia. And what is being measured here, very simply, is the change in the resistance upon the exposure and normalized sensor response. Now, most of the chemoresistive sensors are microfabricated on rigid substrates. You see here also some examples of how they are afterwards integrated and also commercially used, because at the moment we have a lot of commercially used gas sensors, especially with metal oxides. Now, as we're seeing, printing, especially also printing on unconventional substrates, enables a lot of advantages. So first of all, in terms of low cost and usage of materials, scalability over large areas, the possibility of having custom designs with rapid prototyping, and sustainability, especially if we look into materials which have the specific properties. However, this is not for free. I think Vincenzo nicely illustrated this in the introduction, but this comes with a lot of challenges, which I would like to show a little bit for various materials. So in this very nice roadmap, we kind of highlighted, and all the authors basically on the section, on the chapter on gas and vapor sensing, what are the materials that are used. Of course, metal oxides are the king here. They're the most used functional materials, also used in commercial solutions. However, we're seeing also the emergence of other materials that also can be also operated at low temperatures, something that metal oxides are kind of struggling with, and are printable. And here, I just try to focus on some of the materials quickly, and then focusing on carbon nanotube, as said, and especially metal sulfide materials, metal organic framework materials, and of course, carbon nanotubes. This is a short outline, yeah, talking briefly, really, what are the devices, what are the challenges and the strategies. Here, as said, it is a simple chemoresistive gas sensors, various types of materials being used, very nice performance that can be achieved, but there are several challenges linked to metal oxide. So on one side, the short-term reproducibility, but also stability and long-term drift. And one of the most important and pressing issues is surely the selectivity, which we will see is affecting also the other devices, which is of course very important if you want to target specific sensing of specific analytes. And important is also to try to have an effective sensing mechanism and understanding what are the problems behind and the physics. And as already said, the operating temperatures are definitely the major bottleneck at the moment. In this section, Barbara Fabri, Elena Spagnoli, and Andrea Rossi highlighted what are the strategies that can be used in order to overcome. Of course, there needs to be work in the future on sustainable synthesis of these materials to have cost-effective and printable metal oxide sensors. And in order to tackle the major, let's say, bottleneck, the selectivity, it is important to work on machine learning, artificial neural network, also the use of electrical impedance spectroscopy in order to have selective sensors. Of course, understanding of what is happening with operando approaches is also important. And to also have new insights into the gas sensing mechanism with molecular dynamics. I think here it would be, we could be talking a lot about this, but I want to really briefly highlight these other technologies to focus more on carbon nanotubes, where we have been working recently. And metal sulfides are less popular, let's say, for gas sensing, but still have been gaining a lot of attention recently because they have a high carrier mobility, they can be operated at low temperatures and have a very high surface to volume ratio, especially in the case of 2D structures. They are used not only for chemoresistors, so for gas sensing, but also for transistors, heterojunctions, and so on. And there are various forms from the 0D to 3D. Here also there are challenges in terms of understanding better what is the sensing mechanism to optimize the print deposition, which is still an open issue, improve the sensing performance, and most importantly also the stability. And here, as highlighted again in another section of this of the roadmap by Andrea Gallardo, Matteo Valt, and Barbara Fabri again, to overcome this bottlenecks, it is important to gain more understanding on the sensing mechanism, improve the sensing performance, and also the synthesis route for the print deposition, and work on advanced design. But there is it's a very interesting field. Moving on to the other and the last, let's say, example before the carbon nanotubes I want to give. This is another very interesting class of materials, metal organic frameworks, which are gaining interest now in a lot of different sensing devices, because they have a good sensitivity and also enable selectivity. Here we have again various types of 2D conductive MOF composites, and MOF-on-MOF architectures. Besides the advantages, there are also here various challenges to be overcome. So the material stability, but also the material reusability and the sustainability itself of the materials is something that needs to be better understood and developed in the future, as well as to have printed devices also have an optimal dispersion. And here, as highlighted again in this section by Almudena Rivadeneira and Sara Rojas, the two main aspects to work on are, on one side, the functionalization during the MOF synthesis. The MOF are a very nice materials that can be combined and do very interesting for sensing, and also to work on the ink formulation. So with that, I'd like really to switch to the main part of this talk on carbon nanotubes. And we have listened to interesting talks on 2D materials, like, for example, graphene. And here we're talking about the rolled up version of graphene now, which is available, let's say, in two possible configuration, either as single word carbon nanotubes or as multi-word carbon nanotubes. It has, of course, because of the structure, a very high surface to volume ratio, which is interesting for gas sensing in general, for sensing, good electrical, but also thermal conductivity, flexible and low weight devices are possible, and also high absorption capacity. And what happens, what's the working mechanism for the chemoresistive gas sensors is the formation of a Schottky barrier between the carbon nanotubes and the analytes, either intercarbon or also intracarbon nanotubes. Thanks also to this very nice high surface to volume ratio. Interesting, this is extremely printable in the sense that there are various techniques that can be used. Here I'm just showing what are our techniques, or at least what we are using in our lab in order to fully print the devices. So not only the active materials, but also the electrodes. And in particular, we're working on either both contact and non-contact techniques, and digital, and also, let's say, mask-based techniques like dispense printing, screen printing, inkjet printing, and spray coating. As said, nanotubes are interesting because they enable low temperature gas and vapor sensing with a high sensitivity and also fast response time. But also here we have several bottlenecks or challenges, let's say, that we need to overcome in terms of selectivity, drift, and also recovery time that need to be addressed, as you see also here from the picture. What we have been working recently in our lab in the University of Bolzano is on optimizing the spray coating deposition of carbon nanotubes. In particular, you see here some AFM images of different layers of carbon nanotubes, so 8 layers, 12 layers, or 22 layers, all printed on flexible substrates, in this case polyamide, and also working on various printing techniques for the electrodes, for the interdigitated electrodes, with dispense printing, screen printing, and inkjet printing, and characterizing them for ammonia detection. I mean, we were especially interested in ammonia detection for health application, as I will show you in one of the final slides. So this is those are the pictures of the various printed devices. This is thin sprint printing, screen printing, and inkjet printing, and we have been looking in particular, Sahira, in this paper recently published, on the characterization of the different devices towards different concentration of ammonia, but also trying to look at what are the other characteristics. So what's the printing time needed, the cost of the printer, the type of consumables, the waste of ink. We're talking about sustainability clearly, but also the time needed for the use of the machine. So try to find an optimal in terms of performance, but also in terms of other characteristics. And the let's say the application that we try to tackle with that is linked to the human gastrointestinal tract, and in particular we have tried to use our carbon nanotube gas sensors inside an in vitro simulator of the gastrointestinal tract, the so-called SHIME, where we have different biomarkers and different gases like also ammonia, and that allow us to look at the lifestyle and feeding pattern and also the toxicity, and ammonia is interesting, particularly interesting. So the idea is really to put this flexible imprinted carbon nanotubes directly inside this very harsh conditions. The measurements inside this in vitro system show that our sensors are actually able to measure the gas concentration, so not in particular only ammonia, because you see there are a lot of different gases as the quadrupole mass spectrometry analysis show, and are able actually to track the different phases, also the meals that are simulated, and works particularly nice. This is a sensor also with a PDMS encapsulation, and works both without recovery, so that without active heating, but works definitely better if there is an active heating. And this shows also the possibilities opened up. So I'm really moving to the conclusion. I see the time is passing by. We've seen that gas vapor sensors are especially usable in various applications, environmental monitoring, industrial safety, but there are still various parameters that need to be addressed: sensitivity, selectivity, and response time. And these issues need to further refinement. And how to do them, so how to tackle these challenges, we need, of course, a lot of advances on the material innovation. Sustainability is very important, and the realization of full systems for the final application, as well as working towards standards and commercialization. And with that, I thank you very much for the attention.
Thank you, Dr. Petty, for the inspiring talk, a nice overview on various types of printable vapor and gas sensors technologies, as well as the carbon nanotube-based ones. So if you have any questions for Dr. Petty, please drop her in the chat box and she'll address them during the question and answer session. So now let's turn our attention to printable biosensors, which are also crucial for advancing sustainability through widely available high-quality healthcare. And I'm therefore pleased to introduce Professor Aaron Franklin, who's the Eddy Professor of Electrical and Computer Engineering and Associate Dean for Faculty Affairs in the Pratt School of Engineering at Duke University. He's also an IEEE Fellow, and his research spans the use of 1D and 2D materials for high-performance nanoscale devices, low-cost printed and recyclable electronics, and biomedical sensing systems. Thank you for joining us, Professor Franklin. The floor is yours.
Great, thanks, Vincenzo. It's been great to be able to participate in this webinar. Thankful for the perspectives offered by all of the other panelists, and also to spend a few moments closing out the presentations by talking about biosensors, in particular printable biosensors from carbon nanotubes, and I'll try to use this time efficiently to give some helpful perspective here. So there's already been a great introduction to carbon nanotubes, and in particular their structure, electrical properties, what sort of attributes they have that are particularly amenable for a good sensing behavior. I want to just note that over the history of utilizing carbon nanotubes for potential sensing applications, including biosensing, there's been quite a bit of evolution in terms of the used structures of nanotubes, from single nanotube molecules all the way to the more common thin films of nanotubes that are obtained using printing technologies, like you see down here in the bottom right SEM image of this slide. So with respect to the broad field of biosensors from carbon nanotubes, there are a lot of approaches to implementation, including various electrical transduction approaches, electrochemical sensors, for instance, versus field effect transistor-based sensors. And in this regard, I'm going to focus my comments on transistor-based biosensing from nanotube thin films. From the article that's been referenced a few times, this perspective on printable sensors across so many categories, this is the chapter that discusses nanotube-based biosensing from transistor-type structures. And it's just to point out that there are many configurations, one of which would include some type of electrolytic environment for the gating medium, and then this linker type of structure that is either attached directly to the carbon nanotube film or perhaps through some intermediary like a non-fouling layer that's typically peg-like in origin. And this allows for some biorecognition element to be attached and thereby modify or modulate the signal of the device in a way that indicates presence of a target species. So a number of advantages, but there are also some trade-offs, and there were comments made about selectivity it's not inherent to virtually any of the nanomaterial options that you'd like to select for almost any of their sensing applications. So there has to be some intermediary between the target of detection and the target of transduction, which is the nanotube in this case. And that's often achieved with these types of linkers and addresses at least some of the issues. But in the grand scheme of things, there are a number of challenges that still remain for this space. And this includes getting to a point where we have better reproducibility or consistency in the devices. Utilizing printed thin films of nanotubes actually does aid this particular challenge in a significant way. A tangled network of nanotubes across a reasonably wide width of a device actually does produce a reasonable amount of consistency from device to device compared to, say, just a few nanotubes that are attempted to be isolated into a transistor channel. But there's work that remains. There's patchy density that can occur depending on the printing technique, therefore compromising uniformity. There are issues with respect to the residual presence of binders or other molecular species that came through in the solution phase processing of the nanotubes. And then there's actual functionality concerns such as signal drift. And that's one that I'll spend a few moments on in just the latter part of this talk. So one thing I do like to point out about this field is that there was this review paper written over a decade ago, about a decade ago, I guess, and it suggested that at that time, there were over 17,000 papers published on carbon nanotube-based biosensors. And even if the numbers were a little off, even if they were an order of magnitude off, that is still a massive volume of research literature in one rather specific field. So you can imagine the task of trying to actually provide a reasonable summation of what has been done and where we should be going from here. There's great work mixed into those thousands of papers. I would say there's also concerns to the fact that we've published so much as a scientific community with arguably so little to show for it. And I say that to myself as much as anyone else in the community because we don't have a commercial nanotube-based biosensor. And why is that? And so my group tried digging into this a number of years ago. One of the things we tried to focus on is the reproducible actual fabrication of the devices. That's where printing comes in. I won't spend a lot of time on the motivation of printing. I think that's been well established in this webinar. One of the unique things we do in my group with printing nanotube-based devices for biosensors and other application spaces is we focus on some of the environmental sustainability components. This is an example of a fully printed thin film transistor that uses all carbon-based materials, so graphene for electrodes, semiconducting carbon nanotubes for the channel, and then a carbon-based nanocellulose, the dielectric material, followed by a graphene gate. And these devices are remarkably stable, printed on simple, like paper substrates, and actually show recyclability. So you see the aerosol jet printer printing the various layers, which can be used in biosensors, transistors, and so forth. and then we actually extract all of those constituent inks off of those paper substrates to create fully recycled inks, and then use those purely recycled inks to reprint the same type of devices. So this circular life cycle capability by utilizing these inks shows a lot of promise in terms of lifespan for related applications. And then we also explored ways to eliminate some of the more hazardous solvents that are typically critical for some of these printing processes. In this case, focusing only on aqueous inks from those same constituent materials. The devices here that we do report, they look pretty good in terms of performance, but it certainly is a challenge in terms of achieving similar adhesion and uniformity in printed films from just aqueous suspensions of those inks. So the last few minutes, I want to point out a specific study that we recently did on nanotube biosensors. That this is kind of the setting of the stage for that story. These two plots that you can see here, there's a very important difference between these plots that I will highlight with regards to nanotube biosensors, but the comments I'll make are true to almost any type of sensor, particularly biosensors of different types. So a number of years ago, a colleague of mine here at Duke in biomedical engineering, Toshio Cody, developed an optical biosensor that is printed, where you print antibodies into a peg-like layer called poegma, which has a non-fouling advantage, but also provides a really good seeding layer for holding the antibodies. And then it goes through what's called a D4 process, where you expose it to something like whole blood, and it allows for some dissolution, some diffusion, and if there is a target antigen present, a binding event that allows for detection. In the case of the optical D4, that detection is through fluorescence response due to an attached fluorescent tag. We sought out a number of years ago to take that same concept and apply it to a printed carbon nanotube based biosensor, because we wanted to get away from the expensive and clunky optics of the traditional D4 optical sensor and instead use electrical transduction. So this looks complicated. I'm not going to walk through all the little details, but it's basically a printed transistor with nanotubes with that D4 assay printed on top of it. And you could see data here from about 8 years ago was really encouraging looking. You see the transistor behavior change over different concentration spikes. That's what the vast majority of other biosensor papers had reported. And you could see what we developed as dose response curves, both in serum and even in whole blood, showing this type of response. So the question was this victory? And I think that in some research, previous research studies, this was a point of victory, showing responsivity from the transistor for this target signal. But we tried to be a little more rigorous and careful, and didn't anticipate it taking another 8 years, but it did. We kept studying this and realized that what we had initially seen in a dose response type behavior of our current changes over concentration, if you looked at all of the signal, you realize that it was dominated by drifting signal in this electrical transduction environment. So anything that has the type of sensitivity that a nanotube does is going to be highly susceptible to perturbations in a high ionic strength media, especially if you're trying to show relevant performance in ionic media that simulate blood, for instance, like a full PBS without dilution. So this is a problem. This is a problem because we don't know really what's drift and what is an actual signal from response of target analyte. So we dug into this over the years. One thing we did was we stabilized a lot of the external measurement related effects. There's actually a company that students of mine spun out of the lab that builds these little low-cost systems that allow a stable electrical characterization platform and interface for performing electrical analysis. And we utilize that platform to show that we could obtain better stability. We also explored in depth the passivation layers and other materials that are exposing the device to the ionic media. And you can see that in this work cited at the bottom, an optimization of those interfacial layers. And ultimately, all that together over the course of a number of years and several PhD students, really excellent work, and got to a place where we still have this mostly printed device. There are some other fabrication techniques in this particular demonstration, and this stable platform for testing it. And you can go through a lot of the details on the assembly of the device. It's definitely detailed in this citation that you see at the bottom. But I mostly just want to kind of conclude by showing you how promising things look once you address some of these sources of drifting signal in an electronic transduction biosensor from nanotubes. So what you're looking at are cross sections up here where we have a full, what we call D4 thin film transistor biosensor. You have detection antibodies, capture antibodies, and this black line right here is the carbon nanotube. That's the semiconducting channel of the device. So when you expose it, in this case to a full 1x PBS solution, you see a diffusion of those detection antibodies, and if the antigen's present, an attachment event that forms the antibody sandwich and detection. But immediately next door to that device is this control device. So they're sharing the same overall biological media and milieu, and yet this control device does not have the printed capture antibodies immediately above the nanotube channel. So all other things being equal and simultaneously measured with the full D4 TFT. And here's the result. So similar curve behavior that I'd shown you with nothing but drift in the previous device, but now the open circles are the control device that is literally just right next door to the active biosensing device, which are the closed circles. So in the same timestamps, you can see the difference in the response. And there is some signal variation that exists through each of these concentration spikes, yet you can see the stabilized stepwise behavior that is ultimately desired in order to gain confidence in a target concentration being read from the device. And you can see assembled into a more traditional dose response curve on the right, where you also see the presence of some of those fluorescently tagged detection antibodies. In the control case, there's none, and in the full case, there's a lot. So that's this one specific story amidst thousands of papers in the nanotube-based biosensing community, where you could see the story arc of going from the curve on the left to the curve on the right. I think it's worth asking whether or not other sensors that are reported in the community suffer similarly from a drift-dominated signal rather than a target signal with respect to the sensing. And my last slide on this is just to point out that I think as a community, I know this is really wordy, but after spending nearly a decade digging into this problem, really laser focused on something we felt was truly going to be an important step forward for the community. There are some recommendations we list here. There's also some hopes for next steps. And I tell these to my own research group students as much as to the community. We need biosensors, nanotube-based biosensors, printed, that do things more like what I have in the bottom right. Create a dose response curve where every single data point step is a totally different device. That is not just sequential aliquots of concentration increase into one same solution and device, but something that shows enough reproducibility and robustness to actually yield even off different platforms. So I just want to acknowledge excellent research from many students over the years that contributed to a lot of this related work, and appreciate the attention and happy to answer questions with whatever time we have.
Thank you, Aaron, for the very intriguing insights and for reminding us how much reproducibility is a key thing in developing printable sensors. So if you have any questions for Dr. Franklin, please drop them in the chat box as well at this time. And indeed, it is now time for our exciting question answer session. We've ended all our panelist talks, and so it is really our turn with the panelists to answer some of the questions. And if you have more, please drop in the chat box at this time. So let me start with a question, and I invite actually all panelists to share their videos as well, so we can all appear on the screen here. So I'd like to start with a question that deals with, we've received that deals with 2D materials as well as graphene sheets, of course. And the question is about how can we ensure orientation of the 2D materials or graphene sheets while printing or with printing and coding methods. And so I guess I'll ask Professor Hersom as well as Professor Young to address this question.
Yep, I'm happy to take that. So I think unlike carbon nanotubes, 2D sheets have a degree of freedom in this plane, which is not so critical. I think what's important is for them to go down flat and not at some other angle, Or as I alluded to in my talk, when you get very thin, large area sheets, they can crumple. So that's a concern that you probably don't have with nanotubes, but you do have with 2D sheets. So in our experience, the choice of the co-solvents in the ink is critical, particularly in aerosol jet printing, because you can completely lose the solvent en route to the substrate. And if you lose the solvent en route, then you definitely will have a crumpling problem. So you need to go down damp, but not too wet. So controlling the boiling points of the solvents and the rate of evaporation is critical. But if you do that right, then they can go down flat. You can form sort of deck of cards like morphology, which in a percolating network will maximize charge transport.
That's great. Thank you, Mark. Professor Yang, do you have any addition to what Professor Ursama said?
No, I think that's fine. Just perhaps to make a point that the 2D materials do tend want to lie down flat on in thin layers anyway. So that's a natural tendency. Secondly, if there is some crumpling or defects there, as long as it's reproducible, it'll affect your sensitivity a little bit, but you can calibrate the material, and as long as you can get a reproducible crumpling or whatever, then you can calibrate things and make a usable sensor.
That's great, thank you. And actually, there's another question that kind of is a follow-up to Dr. Yang. So one question is about the portability. So you mentioned at one point optical strain sensors, right? So what is how can we deal with the issue of portability of the optical strain sensors that you mentioned?
Yeah, that's an extremely good point. You don't have to carry a large spectrometer like I showed in the photograph. There are portable Raman systems available now, and it is feasible that there could be handheld portable Raman spectrometers, and that sort of thing could be used for inspection purposes. So that's a challenge, but there's been big advances in spectroscopy and spectrometers, and portable could be the way forward, or have special systems made with fiber optics going to spectrometers for sensing things.
That's great, thank you, Professor Yang. So there is some questions also about radiation detectors, so I'd like to ask Oana to address those. So the questions concern essentially what is the mechanism that leads to the threshold voltage shift in your devices upon exposure, as well as if it's got to do with modulating the dielectric as opposed to other layers in your device. So
yeah, very good question. And because of the time limitation, I was not able to show that. So we tested the response of the dielectric as well, and we were not able to detect any changes in the capacitance, dielectric constant. Anything we measured, it seemed to stay constant as response to radiation. But then we also did structural studies, so grazing incidence, X-ray diffraction, and we also did photoluminescence. And then by putting all of these results together, we think that we have the formation of electronic traps as a response of radiation, and this is an irreversible change. That's why the threshold voltage shift is stable. Now we are still to understand exactly how, the one-to-one correlation between the density of electronic traps and the dose of radiation, but there seems to be a relationship between the radiation dose, the nature of radiation, and the overall density of trap states that form in the material, but it's still work in progress.
Mm-hmm. Thank you, Anna. All right, moving on, there's a few questions about gas sensors, and so I'd like to ask Lisa to address those questions. So it concerns metal organic frameworks, but I guess this question does apply to also other types of gas sensing materials that are printable. So it's got to do with the fact that recovery might be a challenge at room temperature, and recovery may be extended to 30 minutes without reaching the baseline. So have you seen this for, well, if you're familiar with the metal organic framework literature for gas sensing, or even in the system that you've been dealing with in your lab?
So, I mean, I'm less familiar clearly with the metal organic framework materials, but I think this is pretty typical in various gas sensing materials. So we've seen this with the carbon nanotubes, and this was also shown in the slide with the application, basically with the temperature, the active recovery. This is way faster. But of course, we would like to have something where we don't need active recovery and we don't need heaters integrated inside the device. So I think that's clearly with the metal oxide, you need to have the high temperatures for the operation, otherwise you don't have a high sensitivity. So that's definitely a big problem in trying to tackle this.
And concerning carbon nanotubes, have you tried investigating how the number of walls in multi-walled nanotubes influences the sensing characteristics for the ammonia sensors?
So we didn't. We always use in our lab single-wall carbon nanotubes. In literature, there are many examples also of the multi-wall carbon nanotubes. Clearly, you have more of this surface area differences, but also then the electrical characteristics changes. So we're very happy with the single-wall carbon nanotubes. We use them for many applications, honestly, and also the printing works pretty nicely. But there are clearly differences among those.
Thank you, Luisa. We're now going to touch on the topic of printable biosensors that Aaron shared about. And the question is specifically regarding any potential drawbacks, so water-based printable ink, like getting washed off or temperature sensitivity. So Aaron, the floor is yours.
Yeah, thanks, Vincenzo. It's a great question. And honestly, regardless of the application, if it's a printable device, particularly one that was derived from an aqueous ink, then it's going to have some susceptibility of residual water solubility in, potential exposures that come thereafter, or even in the multi-step printing fabrication of a more complex device. If you're printing layers, that a device in a thin film transistor that requires multiple layers that have stacking, there's potential for resolubilization of some of those underlying layers when you're fabricating. So obviously there's some careful processing that has to be employed for minimizing that in fabrication, and then in application, it would also require some type of passivation mechanism or other ways to limit the exposure there. I will note though that if there is sufficient sintering related processes, post-print processes of any type, Mark mentioned a couple with respect to the difference between photonic and thermal annealing and things that can drive off some of that residual that was used for the initial solubilization in the ink, that will reduce the susceptibility of further, intermixing or solubilization in subsequent exposures. So the trade-off has to be managed a little carefully, but I think it's doable.
That's great. Thank you, Aaron. Yeah, we have some questions also that sort of concern all technologies that have been discussed today. So I'd like to open the floor for discussion among all panelists. And so one question concerns about whether the inks that you have talked about, that you focus in your research, whether they are already applicable to e-textile, to wearable sensors. So I guess let's go in order, starting from Mark, in the same order that we presented. If you can say a bit about whether your inks or your technologies have already been demonstrated or are in the way to being demonstrated towards e-textile and wearable sensors.
Yeah, so we've done some work, not a lot, but maybe enough to prove the concept that you can take these inks and draw them into fibers, which I think are then amenable to incorporation into textiles directly. So that is one way to do it. The other is to sort of do the printing on top of the textile. There, the issue often is that your ink will be soaked into the interior of the textile in a way that's not very well controlled. How we've gotten around that is to first do a printing step which creates a barrier to that seeping issue, and then you can print on top of that. So there are ways of getting there, including straight to fiber or printing on top of already formed textiles.
Thank you, Mark. Anyone else who wants to share their perspective on this question? Yes.
Could I just say that I don't think really strain sensing is that relevant to textiles. I don't think it's essentially something you might want to do. I may be wrong there, but so I don't think that really comes into it.
I guess you would be generating a lot of signal every moment you move around in your textile.
Yeah, I mean, it's fairly obvious when textiles move, yeah.
Yeah. All right.
I would like to say a few words about the materials that I covered. So I'm not aware of textiles integrated with radiation dosimeters or detectors, but organic semiconductors have been incorporated in various wearable type of applications. But just I'm not aware of radiation detectors.
Thank you, Anna. Anyone else wants to share their thoughts on this? Otherwise, we can move on to the next question. Hearing no other objection to this, then I guess let's move on to the next question, which concerns about essentially biotoxicity of the materials that you've been dealing with. I guess particularly in regard to, say, applications might be in vivo in some cases. So could you, I'm kind of addressing this question to all panelists, if could share your perspective on the biotoxicity of your inks, or more generally the technologies that you've been dealing with. I guess we'll start again with, well, actually we'll start from Aaron, since you're doing biosensing, it's more relevant, but of course everyone else can jump in at any time.
Yeah, I appreciate that. So I would say there's sort of two sides to this, right? Like if it were an in vivo application, then there'd be a whole different type of sensitivity to have and evaluation of cytotoxicity to consider. In the case of nanotube-based biosensors that I specifically discussed, the vast majority are going to be in vitro and just operating external from the body and doing measurement on an as-needed basis. So I don't know that there is sufficient volume of work about in vivo possibilities on that front. I will say that for carbon nanotubes in particular, and many others on this panel can comment of the arcing story over the history of nanotubes. It has the messaging has changed, I'd say, over the years. There were a lot of initial concerns, I'd say, in the 2000s about cytotoxic effects of carbon nanotubes, particularly risks of inhalation related carcinogenic effects. A lot more of the evaluation of actual use case of carbon nanotubes when controlled just as properly as you would control any material that is being processed, especially in mass, is it is controllable cytotoxicity. In other words, I think that within reason in a fabrication procedure, any of those risks can actually be mitigated in ways that are not all that different than what is carried out with existing materials. So that sounds a little bit like an excuse, but it's just a reality that most materials that we interact with on a daily basis have some cytotoxic effect to them, and we just know how to manage our interaction with them. And the same would be true with nanotubes with regards to how they may be integrated in future devices.
Thank you, Aaron. Anyone else wants to share their perspective on this point?
Yeah, I can take a couple more comments. So one is the solvents that are used. And in 2D material field, it's very common to use high boiling point solvents like NMP, which undoubtedly have some ecotoxicity issues, which I actually showed in my talk. Switching from NMP to ethanol, basically eliminates that problem. And that's why we insist on using ethanol. It's harder to disperse nanomaterials in ethanol, but using cellulosic polymers, you can get past that. So that's one comment. The other is we've worked both with Northwestern University Medical School, Scott Budinger in our pulmonary division, and also with UCLA Medical School, Andre Nell, who's the chief of nanomedicine. They looked at both graphene and molybdenum disulfide. With molybdenum disulfide, I remember Andre coming back to me and saying, "Oh, we're not seeing any response in any of your samples." And he was disappointed because toxicologists want to see a response. I was pretty happy about that comment. So molybdenum disulfide seems to be quite benign. Graphene also is relatively benign. The issue that arises is when aggregation occurs. So if graphene remains well dispersed, then it can be cleared via macrophages with little to no toxicological effect. If it begins to aggregate, then things become more complicated. So I think the key is keeping your materials well dispersed. And if you do that, then most of the toxicology issues can be mitigated.
That's a very interesting point, actually. I wasn't aware of it. It's really a nice, intriguing point. I guess organic semiconductors, Anna sort of mentioned already about sort of biocompatibility, I believe, right? Is this something, Anna, you would like to expand on, or?
I think with organics, I mean, there's such a wide variety of the materials, right? So then these properties will differ from material to material, and they can be tuned so that they are biocompatible. That in particular, with respect to organic electrochemical transistors, which have been used as different types of sensors. So yeah, some organic materials can be biocompatible.
Mm-hmm. All right, thank you. Anyone else like to comment on this point again? Otherwise, I've got one last question, which is the million-dollar question that everyone would like to know about, which is about what is left for us to see those kinds of sensors you've described in your presentations, to see them out there in the market, or to see them much more widely adopted than they are at the moment. Anyone would like to address that question?
Well, I'll take the first stab at it. So, you know, the inks that I described, not all of them are commercially available, but some of them are commercially available from companies like Millipore Sigma. And at the scale at which they're being produced, they're pretty expensive. So you need to scale up. And that's where, in our opinion, any batch process creates a significant barrier to scaling. So getting full continuous flow processing from exfoliation to separation to concentration, I believe is game changing in that regard. And I sort of showed that in my talk. You know, the proof's in the pudding. We have to go do it at scale and get the price down. If that works, then I think you at least have addressed that barrier. Next step, I think Aaron talked a lot about, is you got to be able to print devices that work every time, and that's a challenge. And progress is being made, but we need to produce many more devices to get good statistics to meet the demands of industry.
Thank you, Mark. That's really valuable. Anyone else before we wrap up?
I think with organics, a big challenge is also stability, being able to reliably fabricate stable devices so that you can separate between the impacts of radiation or sensing of various chemical or biological species and just like aging of the device. That's critical.
Thank you, Anna. I guess in the interest of time, we'll wrap up now. So thank you again for staying until the end of the webinar, and for all the panelists and all that. So I'd like to mention that please feel free, if you didn't get your questions answered, please feel free to reply to the GoToWebinar invite you received, and we'll make sure to pass them on, those questions that you might have, to the appropriate speaker after the webinar is over. And before we wrap up, again, I want to give a big thank you to everyone who made this event possible. You firstly as the audience, our panelists, and the team at IOP Publishing. And I'd also like to mention that if you would like to watch the webinar again offline, after the meeting itself is over, you can also go back to the same registration email and you can access the recording right there. So you can really go back to it and digest it fully. I'd also like to encourage you to check out the free roadmap on printable sensors available on the Nano Future website. It's a great resource to explore further and potentially even to find answers to some of the questions we couldn't cover today. And by the way, a special thank you goes also to all other co-authors who contribute to this publication that are not here today. And as we close, I hope that today's webinar, alongside the roadmap, has inspired you to explore or potentially use or even contribute to the world of printable sensor technologies, joining forces for a more sustainable future. Thank you once again for joining us, and take care.